Hello dear students, welcome you all for transmission and distribution class. So continue with the third module, that is the performance of the transmission line. In the previous classes we have seen short transmission line and medium transmission line. In the medium transmission line we have seen the end condenser method. Today we are going to see the nominal T method. So in this method the whole line capacitance is assumed to be concentrated at the middle point of the line, and half of the line resistance and reactance are lumped on its either side. In previous case, end condenser method, total capacitance are lumped at the end, that is at near the receiving end. But here, total capacitance is lumped at the middle point, means such a way that the one part of the capacitance is having R by 2 and XL by 2. Other part of the capacitance is having R by 2 and XL by 2. So means total resistance and inductance has made equal halves. In between capacitance is added. So you can see this figure. Vs is R by 2 XL by 2, then is flows, then in between capacitor will come IC will flows there. Next once again R by 2 XL by 2, where the current IR flows to the load. It is very clear that IR is the load current or receiving end current, V1 is the voltage across the capacitor, IS is the sending end current, R is the resistance per phase, IC is the charging current, XL is the reactance per phase, VR is receiving end voltage, C is capacitance per phase, VS is the sending end voltage. So we are going to take VR as the reference as previous, that is we are receiving end voltages, we are considered it as the reference one. So we will write VR plus J0. Assuming that load is obvious RL, that is inductive, we will write IR is equal to IR cos phi r minus J sin phi r, where phi r is the angle between IR and VR. Okay. So now we need to find the what is the voltage across the capacitor, that is V1 is given by, you can see here in this figure, VR plus the R2 XL2 drop. Okay, that is the current flows there is IR, so we can write V1 is equal to VR vector plus IR vector Z by 2, because RL by R by 2 plus XL by 2, or RL by 2 plus J XL by 2, we can take this as totally J by 2. Okay, so I can write here IR into J by 2, or whatever IR is, we are having cos IR into cos phi r minus J sin phi r, and Z is nothing but Z by 2 is nothing but R by 2 plus J XL by 2. Okay, we know that IC is equal to J V1 omega C, and IS sending end current is nothing but IS is equal to IR plus IC. You can see there, when IS comes here, when C is there, IC one part is flowing and remaining current flows as IR. So togetherly IS we can call it as IC plus IR, or VS is written by, once again, sending end voltage is V1 plus the drop in the remaining R by 2 and XL by 2. We can write that as V1 plus IS into Z by 2. So the nominal T method phasor diagram is shown here. So the step by step how to draw the phasor diagram I will explain here. You can see there. First, VR is taken as the reference. Usually, as I will tell you, we will take the VR as the reference only. We know that IR lags VR by some angle phi r, because considering the load as the inductive RL. You can see I have drawn the IR there now. Okay, with an angle phi r. It is very clear now. Okay. Next, what is that? When IR flows, it causes a drop in IR R by 2. Okay, so where the drops will be, the resistive drop will be in phase with the current. So we know that while finding the VS, or finding V1, we know that VR plus IR into R by 2 plus JXL by 2. First is IR into R by 2. Now IR R by 2 is what VR is added with the in the phase with the current IR, that is IR R by 2. When IR flows through the reactance, it causes IR XL by 2. That drop is perpendicular to the current IR. So I have drawn there 90 degree to the IR R by 2 drop. Okay, so we see the figure, that fourth figure now, how it IR XL by 2 is there. Then the phasor sum of IR R by 2 plus IR XL by 2 is the IR Z by 2. By adding the dotted line, we will get IR Z by 2. So if you connect the starting point to that point, that is the total vector of V1, that is the voltage across the capacitance. Okay, now we know that IC leads voltage VR by 90 degree, because the IC is purely capacitive current, VR is the voltage across the load. So IC is having 90 degree to the voltage VR. So I have drawn IC is 90 degree to the VR, and that IC is added with IR to get IS. No, that's what IR plus IC. You can see in this figure, it is very clear. it is 90 degree to VR I have drawn from the end point of the IR. And now vector sum of IR and IC is same as IS, you can see in this figure. Okay, so now if IS flows in the first half of the circuit, we are knowing that IC flows in the first half, there is once again drop of ISR by 2 plus J ISXL by 2. So the same drop starting from the V1 I have drawn here, same as the VR is added with the first half drops. Now it is the second half drops. So after drawing that one, the total point of the summation of the ISR by 2 and ISXL by 2, we will get ISZ by 2. That is added with V1 will get us the Vs. So directly I have added the line. So this is what the way to draw the phasor diagram. So step by step drawing of phasor diagram I have shown here, starting from the VR as a reference. You can draw by your own to get this phasor diagram. Okay, we will see one problem. Missing 3-phase 50 Hz overhead transmission line has 100 km long, has the following constant, that is resistance per kilometer per phase is 0.1 ohms, inductive reactance per kilometer per phase is 0.2 ohms, capacitive susceptance per kilometer per phase is 0.04 into 10 raised to minus 4 Siemens. Calculate sending end current, sending end voltage, sending end power factor, transmission efficiency when supplying a balanced load of 1000 kilowatt 10,000 kilowatt at 66 kV power factor 0.8 lagging using the nominal T method. This is the nominal T method because we are using the capacitors at the midpoint. Okay, now we will write down what are the things given. Okay, anyhow per kilometer value is given. We are having the total kilometer is 100, so multiplying by 100 we will get the actual resistance and reactance and capacitance. Okay, of all the values we are multiplied by 100, will get capacitance resistance is 10 ohms, reactance is 20 ohms, and the capacitance is 0.04 into 10 raised to minus 2 Siemens. Receiving end voltage is they are given 66 kV 3 phase, divided by root 3 we will get 38,105 volts as the receiving end phase voltage. Receiving end power is given 10,000 kilowatt. Okay, and sending end power factor is given, that is 0.8 power factor lagging. We need to find out what is IS. Before finding IS, we should know what is IR, IC and V1. Okay, so VR is unknown, means we need to write as it is, VR plus J0. We are calculated 38,000. So we need to calculate IR using the PR. 3-phase power is given, that is PR by 3 VR cos phi R. We are going to get the IR. So IR value you got as 109.34 amps. Or cos phi R is known, so we can get the value of current in phasor, that is 109 angle minus 36.86 we got, because cos phi R is 0.8, that is angle phi R is 36.86. obviously the current is lagging, means you can take the angle as minus 109.34 angle minus 36.86. Impedance is already we need to calculate 10 plus J20, because 10 is resistance and 20 is inductive reactance, and J by 2 is divided by 2, will get 5 plus J10. Or if you want that one, you can convert it into polar formula. So we will going to get 11.18 at angle 63.43 ohms. Now we need to find out what is V1 first. V1 is what? VR vector plus IR vector Z by 2. Put all the values, we will get the V1 as 39.202 angle 0.799 volts. Then finding the current IC, that is JYV1, we are knowing the formula. Put all the values, we will get the values ICS minus 0.218 plus J 15.6 amps. Find the IS, that is IR plus IC. This is what the first case we got. We were finding the IS values. 100.56 is the sending end current. Once we find the sending end current, we need to get the VS, that is the sending end voltage, that is VS is equal to V1 plus IS by Z2. Put all the values, we will get VS as 40,152 at an angle 1.668 volts. Or line value, if you want that one, multiply it magnitude with root 3, we will get 69,462.9 volt as the sending end voltage. So sending end power factor is we need to calculate IS angle we are having, VS angle we are having. Actually sending end power, these two angles are with respect to VR, because we are taken VR as the reference now. So to get the phi S, we need to have, by seeing this figure, you can see VS is having an angle of 1.608 with VR, and the IS is having an angle theta 2 with VR. So adding those two angle, we will get the 31.478 degree, that is angle between VS and IS. So cos phi S is 0.852 lagging. Transmission efficiencies we are knowing this is the regulation, I think. Transmission efficiency is what? Sending end power minus sending end power divided by the receiving end power is transmission efficiency. Here the fourth one is the regulation we are found out, that is sending end voltage minus receiving end voltage divided by receiving end voltage. We are getting 97.3. Okay, so you can calculate this one by your own once again to get the result. So the remaining problems we will see in the next class. This is the one of the method that nominal T in medium transmission line, because the total capacitance is taken at the center point. Okay, if you find any difficulties, you can call me. Thank you.